Hi, my name is Logan Sparvero, and this is for ME56900, Mechanical Behavior of Materials. And this project will be regarding a change and a redesign to the 1954 to 1977 Ford and GM fuel tank system. So today's car prices are drastically increasing. These mid 20th century Ford and GM cars are extremely cheap, but they're not a smart idea. And that's because they're very safe and they're very unsafe. And their major fail to that was their faulty fuel system that was seen in a lot of them. The Pinto is the most famous example, which is why its pictures are included. But this was also prevalent in the Cavalier, the F-150s of the era, the 250s as well from Ford, the smaller Ford sedans, the wagons from GM. It was quite a prevalent problem for many of the American brands, but most prevalently the Ford and the GM ones. Uh, so the fuel tanks were made out of cheap steel that would rupture under low impact speeds, and the designs were faulty. Uh, they were mounted way too low, and they absorbed little to zero force. So the NHTSA has done research on regulations and materials for modern cars to determine what is safe and what is not safe, and they keep on changing those regulations. And their research and their statistics play a huge part in the design of this project. The missing part of the project, though, the problem to solve is to find a stronger, lighter aluminum for support structure and finding a way to implement it into a lot of these vehicles and be kind of a universal fit. So that is kind of what the objectives are, what I'm hoping to solve, a redesign to fit those premises. And to fit those premises, I need to make first design a fuel tank that is a universal fit, and then run a few soft engineering analyses on them to prove the concept. And the ideas is equivalent stress, equivalent strain, stress safety factor, fatigue life, and fatigue safety factor. Fatigue life will give us the number of cycles and how much it can withstand. Stress and strain is the impact force it can withstand. The stress safety factor and the fatigue safety factor are its reliability. So there's a lot of things we're going to be touching into. So this was the design. It is a universal fit into the bottom pan of these cars in the trunk, and fits underneath a support brace for the rear axles. So it's in a very safe location. And this is the mesh you can see on it. All the details are here. We had a 0.001 meter size, meter element size for the mesh used to get a very smooth and a very precise and accurate analysis on it. The number of elements we have is 58,687, and the nodes is 119,210. So it's a pretty precise analysis when running all these forces. So these are the governing equations we'll use in the following analysis that was run on this project. You can take a look at all of them here. Most to all of them were done on the computer analytical side. So not a lot of pencil and paper and hand calculations were made, which takes human error kind of a little bit out of the equation. So for boundary conditions, I set a force on the outermost wall, which is where the fuel will most likely get hit, is in a rear end collision, of 400 newtons. This was in accordance to the NHTSA and their recorded database on how much damage a fuel tank really takes within an average accident in the US. Since there is a support brace on the bottom of the fuel cell and it is screwed in on the top, both the top and the bottom are going to be fixed supports, meaning they don't have any degrees of motion, because not only is there a brace there, but it would be strapped around that brace with metal straps, which is usually how fuel cells are installed. So Other boundary conditions are due to licensing and limitations, the filler had to be removed for the analysis. And that is that portion right there with the air inlets. And then there is supposed to be a circle there, which is a fuel filler, but it did not transcribe over into ANSYS. So that was replaced with a blank with a flat piece of aluminum to aid in the analysis, because my license would not allow me to do an object like with that many nodes and element sizes. It was solved as a hollow to show the analysis of the situation of least structural integrity, in addition to the fact that modeling fluids and ANSYS is a pretty difficult and complex process. So for the material properties, it needed to be very strong, very lightweight, as to not mess with the weight or the distribution of the vehicle, besides the weight of the gas, of course. So you want to be as light as possible because you are adding that fuel in. And so the material I decided upon is 7075 T6 aluminum. And I knew that from past references to just how this project was inspired is a lot of the times what you see in the commercial area of the automotive field is what happens in the sports side of it, the racing side of it beforehand. And that's what we're seeing with fuel cells. It's kind of a modern concept, but it's seeing more and more into sports. And we're first starting to see fuel cells become commercial on the commercial side of automotive field with the new hydrogen cars that are coming out. So this one is also used a lot in racing. It is an airspace grade aluminum. It is used for fuel tanks and fuel systems in racing because it is also used on fuselages of rocket ships. So on the following page, we can see all of the material properties and all of its mechanical, thermal, and most properties you can know about a material. These are all inserted into ANSYS, of course, to run the analysis. So talking about analysis, this is our first one. This is equivalent elastic strain. So we can see not a lot of strain is on here. The other sides, as well as the top and the bottom, are completely blue at the minimum. And the maximum isn't very high either, and that's located at the edges as well as the center of the foremost facing front of the fuel cell. But no critical areas, no areas of fracture, and that can also be seen while looking at the stress analysis as well. Very low stresses on the object. Stress safety factor we can also see is very good. It is very high with a minimum of 10. Results in discussions. Again, we're going to talk about fatigue life. Fatigue life is 1 times 10 to the 8th cycles. A cycle was set at 1 week. So that is approximately 14 years minimum cycles. So, and that just happens on the foremost face of it. And this is while withstanding those impacts. So while withstanding these impacts, it can last 14. Now we're going to talk about the fatigue factor safety. Same deal. It's not as high as I would like, but it is still 5.663 at the minimum. And it is, it is on those edges while withstanding this force, which is the average force of impact on an accident. So you can see that the fuel cell is extremely strong, and going into discussions that is mostly because of its shape. Now, while fuel tanks are fit to bend around the car and fit the most amount in such a small place, if you get a big fuel cell and find an empty space and put it there on a larger existing, more vacant chassis, a solid square distributes the load and the stresses a lot better than an object such as this. And the trends show that the 7075 T6 aluminum is a great material. It is extremely strong, has a very high fatigue time. It is overall a great form of aluminum. And it couples with the fact that it's easy to manufacture and produce and manipulate as a material. So it has incredible materials, and we can see that in the analysis. The overall effect of safety and deformation and stress show that it is a valid and leagues better replacement to the existing fuel tank. It served its purpose. It meets well and above the NHTSA's standards for safety in a modern vehicle, let alone retrofitting this into a older vehicle. And this is with direct force impact. The reason why a bash bar was not included was because on analysis, while just running the fuel tank, it was able to withstand so much impact force that there wasn't really a need for a structural brace around it, that it could take the grunt of the impact of a car. Now, it is still shielded by the rear frame, so most likely or not, it will not get punctured. And even if that is the case, most fuel cells like this have a auto shut off connected directly at the pump. So for summary and recommendations, what we did here was we tested a replacement fuel cell for a series of GM cars to make cheap and affordable cars more effective to be used nowadays. And we proved that design through soft engineering analysis. And what I would recommend to do is continue the analysis, but generate it with fuel included inside of the cell and run kind of the same analyses. Raise the mounting points on the vehicles. So it should be lower the mounting points on the vehicle. Raise the mounting points on the vehicle so it could be even higher and more safe and impact resistant. A little side note, while the references are displayed, no time dependent analyses were made, and no animations were included just because of power. Google Slides kind of limitation on that. It couldn't work properly. And then secondly, the time involved analyses weren't really a thing because I was testing impact of car accidents. Because if it can withstand that force, the concept is that it can withstand minor changes, and it was going to be near impossible to calculate the kind of vibrational disturbance or the load that it's under normal usage for years amount of time, since cars are so different and this was supposed to be universal. But this has been my project. I hope you have enjoyed, and thank you very much.